Residuals. A residual value is the difference between an actual observed value y, the one that we're given, and the corresponding predicted value y hat, the one that fits on our least squares regression line. Residuals are just errors. They are found by finding our observed value and subtracting our predicted value, y minus y hat, for a corresponding x value. Let's look at an example. A least squares regression line was fitted to the weights in pounds versus age in months of a group of many young children. The equation of the least squares regression line is y hat equals 16.6 plus 0.65 t, where y hat is the predicted weight and t is the age of the child. A 20-month-old child in this group has an actual weight of 25 pounds. So that means that y of 20 is 25. What is the residual weight in pounds for this child? Well, first we need to figure out what y hat of 20 is, and we get that by plugging 20 into our least squares regression line. And we get a value of 29.6. So our residual will equal our y value minus our y hat value, which will be negative 4.6. The plot of the residual values against our x values can tell us a lot about our least squares regression line model. Plots of residuals may display patterns that would give some idea about the appropriateness of the model. If the functional form of the regression model is incorrect, the residual plot constructed by the model will often display a pattern. In other words, we do not want to see a pattern if we're looking for a good linear relationship. The pattern can be used to propose a more appropriate model, and when a residual plot shows no pattern at all, it indicates that the proposed model is a reasonable fit to the set of data. Of course, we don't use just the residual plot to make this decision. We also look at our values for our correlation and our coefficient of determination, as well as looking at the scatter plot and how the line looks on it. These are some examples of residual plots. Both of these show patterns. This first one has a pattern of telescoping values, kind of in a horn shaped, and the next one looks almost like a quadratic. So both of these would represent bad models. Here's another example. Suppose we have this data set and the equation is 17.3 minus 0.96x. I want to draw the residual plot. Now before we do that, we need to find all the corresponding values of y hat for each of our x values. So I'm going to plug 2, 7, 4, and 12 into my y hat equation. And this is going to give me 15.38, 10.58, 13.46, and 5.78. So we have our real y's, our observed y's, and our predicted y's. So our residual we'll get by subtracting these two. So we need to get our residual values and then we'll plot them. So 15 minus 15.38 is negative 0.38. 11 minus 10.58 is 0.42. 12 minus 13.46, negative 1.46. And 5 minus 0.78 gives us negative 0.78. So we're going to plot our x values and the residual values onto this graph. Now our residual plots will always be centered around our x-axis. So this will be y equals 0. So here's my x values, and for each one I'm going to plot my residual value. Now most of these are all less than +1 and greater than -2. So I'm going to use that for my scale. These do not have to be drawn to the same scale as your x's. Okay, so for 2, I'm going to be at -0.38. For 7, I'm going to be at +0.42. For 4, I'm going to be at -1.46. And for 12, -0.78. Now, of course, we have only 4 data points, so it's kind of hard to say whether or not we have a pattern in this instance. Here's another example. The following data was conducted comparing score on a measure of test anxiety and an exam score. We're going to go through all of our steps, constructing a scatter plot, finding our least squares regression line, finding our R and R squared, make a judgment on the linear relationship, then look at our residual plot and see if it justifies our answer in part D. So my first step will be to enter my data into the calculator. We have to decide which one is our explanatory and which one's our response score. Our measure of test anxiety should be our X, our explanatory, and the exam will be our response, our Y. So stat, edit, and I'm going to enter anxiety into L1 and exam score into L2. So here's my data. Let's look at a scatter plot of the data. Let me turn off plot 2. And go to plot 1. Turn it on. L1 and L2 are where my lists are. So now let's graph it. And remember, we need to zoom stat when we're looking at our scatter plots. So what I'm seeing from the scatter plot is a negative relationship if I were to predict where the line is. But let's go ahead and draw our line on here. So remember, we're going to go stat, calc, 8, and we have L1, second one. For our X list, L2, second 2 for our Y list, and we want to store our regression equation in, oops, I don't want second on, variables, Y variables, hit enter and choose your Y variable. We'll use Y1 here. Okay, now let's calculate. So here's our values for our y-intercept, our slope, our coefficient of determination, and our correlation. Now let's look at our graph with the line going through it. And it doesn't look too bad. It's kind of where we predicted. Maybe not. I kind of expected it to come a little closer to this top point. Okay, so let's go through and report on our data, and then we're going to get our residuals. So we've done our scatter plot, and we found our least squares regression line. And it is going to be y hat is equal to 68.838 minus 1.0638x. Our R value here is 0.7877. Close to 1, but not very strong. Very strong would be something above 0.9-ish. Our R squared is 0.6205. So 62% of the variation can be explained by our least squares regression line. So based on these values, I would say that there's a pretty good linear relationship on the two. It is a negative relationship It's kind of hard to say strong or weak, maybe more on the strong side than on the weak. Now let's look at the residual plot and see if it justifies what we said. Now to make the residual plot, the first thing I'm going to do is I'm going to turn off the other scatter plot. And I'm going to turn off my y equals. So I'm going to go to y equals, I arrow over so it's blinking on the equal sign, and I just do enter. Now it won't display the line with my data. I don't want that with my residuals. Now I'm going to have the calculator calculate my residual values like this. Go back to your list, stat, edit, and I'm going to put my residuals in L3. Now remember, your residual values are your actual y minus your predicted y. So I'm going to arrow up to where L3 is, and I'm going to hit enter. Now what this is going to allow me to do is put a formula in for all the contents of L3. So here it will be my actual y, which is in L2, minus my predicted y. Now my predicted y's were stored, the formula for them is stored, under our variables y1. So we're going to take L2 and we're going to subtract y1 with our x values, which were in L1, plugged in. So if I type this in where I have the top value for the list highlighted, it's going to fill my list with my residual values. Again, my actual y's, which are in L2, minus my predicted y's, which are y1 with our L1 values plugged in. Now I'm going to hit enter. There's my residual values. They're all calculated for me. I didn't have to do them by hand. Now to see my residual plot, we're going to make a scatter plot, and my x's are still the same x's, so they're in L1, but my y's, we use our residuals, which we put in L3. Now we're going to graph, and we need to zoom. Every time we do a new scatter plot, we need to zoom stat again. And here is my residual plot. So you can see for most of it, there's not really a pattern. We have 2 points that are kind of offset from the rest. This one has a very large residual value because it's very far from our x-axis, our y equals 0. So this could be an outlier. This one also could be causing problems too. It's not as far above the rest, but its x value is way away from the rest as well. Okay, so what does the residual plot reveal? It reveals that we're probably okay with saying this is a somewhat strong linear relationship, but we might want to investigate further by taking out our outliers. Last, is it reasonable to conclude that anxiety caused poor exam score? Well, the big word here is caused. We can never assume, no matter how strong our linear relationship is, that there is causation between our variables. The only thing that we can assume is association. So association does not imply causation. So we can never make that assumption. Now, since the residuals show how far the data falls from the least squares regression line, examining the values of the residuals will help us gauge how well the LSRL describes the data. The sum of the residuals is always 0, so the plot should always be centered around the x-axis. An outlier is a value that's well separated from the rest of the data, as we saw in the previous example. they will have large residual values. An observation that causes the value of the slope and the intercept of the line to considerably change is called influential. Let's look at one more example. Johnny keeps track of his best swimming times for the 50-meter freestyle from each summer swim team season. And here's his data. We want to investigate our least squares regression line model. So we're going to go through our steps that we did with the previous example. We're going to look at our scatter plot, find our least squares regression line, look at our values for r and r squared, and look at our residual plot and see whether or not we think that the least squares regression line is a good model. Okay, I've entered his age in L1, those will be my x variables, my explanatory, and the time in seconds in L2, those will be my response or my y's. So let's look at our scatter plot. We'll turn it on, L1 and L2, and let's graph, zoom 9. And it looks like we've got a pretty good negative linear relationship. So let's put our line on there. L1, L2, and don't forget to store it into Y1. That helps considerably when we're doing our residuals. So here's my values. So here's my y-intercept, my slope, my r squared, and my r. My value of r does confirm a strong negative relationship. 84.6% of the variation can be explained by our least squares regression line. Now let's graph it with our line on top. And it looks pretty good. Now let's look at our residual plot. Remember, to make our residuals, we're going to create a third list in L3. So arrow up to L3, hit enter. Now it's our actual y's, which are in L2, second 2, minus our predicted y's, which we'll have it calculate by doing variables, y variables, choosing our y variable that we stored our equation in, parentheses, and then our x list name, which is L1 here. When I hit enter, we filled up with our residuals. Now let's create a scatter plot of our residuals. So go to snap plot. We'll just make them again in plot 1. So we're going to just change our y list to L3. Now before I do this, let's turn off the equation. Arrow over to your on the equal sign and just hit enter. Now we're going to do graph. And we're going to have to zoom 9 again. So here's my residuals. Again, we don't have a lot of data. It's hard to make a decision about whether or not there's a pattern when you don't have a whole bunch of data pieces. But what we should notice is this point down here. It has a much larger residual than all the rest of the data. So this point is definitely an outlier and is possibly influential. Now when I look back at my list, this point comes from this value right here. Now if you know about swimming, your time should decrease as you get better at it. But we've had a huge jump of 6 seconds, which is quite large. So there could have been an error in the timing or recording of his data, or maybe the pool was not 50 meters exactly. Maybe it was a yard pool instead of a meter pool. So I bet if we remove this point, we would have an even stronger least squares regression line correlation.